certain urgent work. We will not take test today, okay? आणि आज आपण ऍक्च्युली कालचा राहिलेला पार्ट म्हणजे काल आपण मध्येच जे सेशन बंद झालं मला काही अर्जंट काम होतं त्यामुळे तर ते सेशन आपण कंटिन्यू करूयात आणि त्याच्यानंतर नेक्स्ट वीक मध्ये आपण टेस्ट कंडक्ट करूयात. ओके, सो अँड आफ्टर कम्प्लिशन ऑफ दिस युनिट वी विल कंडक्ट टेस्ट ऑन दिस युनिट ऑल्सो. ओके, पण त्याच्यापूर्वी मी तुम्हाला सगळ्यांना असाइनमेंट क्वेश्चन शेअर केलेत. ओके, गुगल जी तुमची HTML शीट आहे ज्याच्यामध्ये आम्ही स्टडी मटेरियल शेअर करतो तर त्याच्यामध्ये असाइनमेंट सुद्धा शेअर केलेले आहेत, असाइनमेंट क्वेश्चन. सो मी परत एकदा सांगतेय की ते तुम्ही सोडवायला सुरुवात करा. ओके, ऍक्च्युली 23rd is the last date for submitting assignment on 5th unit. Okay, and then complete other earlier assignments. पण आता 23rd ही लास्ट डेट असणार आहे 5th युनिटची असाइनमेंट सबमिट करण्यासाठी. तुम्ही कुठल्याही पेजेस वरती तुम्ही एखाद्या नोटबुक मध्ये सुद्धा असाइनमेंट लिहिल्या तरी चालणार आहे. यावेळेस आम्ही ते कन्सिडर करू. त्याचबरोबर तुम्ही तुमचं PPP सुद्धा लिहा, कारण ज्या वेळेस कॉलेज मध्ये तुम्ही परत रिजॉईन व्हाल, जेव्हा कॉलेज फुल्ली स्ट्रेंथ मध्ये कंटिन्यू कराल तुम्ही, त्यावेळेस तुमच्यावरती प्रचंड लोड येईल आणि त्यावेळेस मग तुम्हाला काय नक्की करायचं हा प्रश्न पडेल. ओके, कारण आता बऱ्यापैकी गव्हर्नमेंट पण विचार करतोय की कॉलेज आता सुरू करायला हवंय किंवा कॉलेजेस स्कूल दॅट शुड बी स्टार्टेड. आणि तसं जर झालं तर नेक्स्ट म्हणजे काही दिवसांमध्ये कॉलेज चालू झालं तर तुम्हाला प्रॅक्टिकल्स पण करायचे आहेत, तुम्हाला असाइनमेंट्स पण लिहायचे आहेत, तुम्हाला PPP लिहायचंय आणि बाकीच्या बऱ्याच ऍक्टिव्हिटी कराव्या लागणार आहेत. तर त्यासाठी आत्ताच थोडा थोडा वेळ स्पेअर करा आणि तुमच्या असाइनमेंट्स ज्या म्हणजे तुमच्यावरती एकदम लोड येणार नाही. ओके, तो तुम्ही आत्तापासून कमी करा तुमचा लोड आणि जे काही असाइनमेंट्स वगैरे दिलेले आहेत ते सोडवायला सुरुवात करा. तुम्ही कशावरही लिहिलं काहीही प्रॉब्लेम नाहीये. ओके, तुम्ही पेजेस मध्ये लिहा, तुम्ही कुठेही तुम्हाला जे मिळत असतील मार्केटमध्ये तुमच्या जवळपास जे काही अवेलेबल होत असेल ते तुम्हाला तेही नाही अवेलेबल होत आहे तर तुम्ही नोटबुक मध्ये लिहू शकता, काहीही इश्यू नाहीये. ज्यावरती तुम्ही लिहाल फक्त तुम्ही लिहिणं महत्वाचं आहे जेणेकरून तुमची प्रॅक्टिस होईल. ओके, सो कम्प्लीट करा आणि जे तुम्हाला काही प्रॉब्लेम येणार नाही. ठीक आहे, so for today's session let us have the practical, okay, which we have left in between in the earlier session. Okay, so we were discussing about the full adder using structural model. So in a full adder circuitry we in a structural modeling where we are using certain different components and using that components we are building full adder circuitry. So to build full adder circuit using half adder, okay, and OR gate. So there we require 2 half adder and 1 OR gate. So I have shared earlier with you that circuit diagram with a 2 full adder, 2 half adders and 1 OR gate that will make or that will give us the circuit that is a full adder. So as we know that in a half adder circuitry we have 2 input ports and 2 output ports. Okay, that means there is a addition of 2 bits and that gives us output, that is a sum and carry. Okay, so these are the 2 outputs. So when we are considering full adder circuitry we add 2 bits with this at the same time a carry, input carry, that also we are adding to this addition. So that means actually in a full adder circuitry we are adding 3 bits. So there are 3 input ports in a full adder circuitry, okay, and then 2 output ports so that we are getting the output in terms of sum and output carry. Okay, so we are going to perform this experiment. I'll present my window now. Okay, instead of window, I will share screen. Whether my screen is visible?
Yes, ma'am.
Yes, ma'am.
Okay. Uh, so this is a full adder circuitry with a structural modeling. That means here we are using two components. One is the half adder and another one that is a OR gate. Okay. So here in the circuitry, as we discussed earlier, we are giving two input bits, that is a and B, to one half adder circuitry, and there we get output, that is a sum and carry, output carry. Okay. Now this sum in output that is given as an input to another half adder circuitry, one of the input to another half adder, where another input to that half adder is the carry input. Okay. So output of that some output is considered as the output of full adder circuitry, and then whatever is the carry output of both these half adder circuitry, that is OR, and output of that OR gate is considered as a carry output. Okay. So this is the structural modeling of full adder circuit. So that means whenever we want to write a VHDL code for this full adder circuitry, we need to have two entities or two VHDL codes, that is for the one component that is a half adder and another component that is a OR. Okay. So if we have these two codes, then using that two codes we can get or we can write a code for full adder circuitry. So how we can do that, that we will see in this session. Okay. So let us open Xilinx IC. Okay, so again I will start with a new project now, because yesterday's project I'm not going to open it, and I'll start with a new project. Okay, so here now whenever we are opening this Xilinx IC, you can see that there is a one small window opens. Okay, where it is a return, that is a tip of the day. Okay, every time whenever you are newly opening this Xilinx IC, that time this window will open, which will give you a small tip how you can use this software efficiently. Okay, so for that these tips are given. You can read these tips, or otherwise we can close it, and then we will proceed whatever knowledge we have with that only. Okay, so let us close this, and we will proceed further. And then I have already completed this project, but for use I will again use a new project. Okay, so new project. So here I will give this name to this as a full adder FA underscore structure. Okay, so this is the name that is I have given to this new project. Okay, remember that you have to make this top level source type as a HDL. Okay, there are so many options, that is a schematic, then EDIF, NGC and NGO, but as we are going to use HDL language, so you have to make this option, that is HDL, and then go for the next. It is already there, so I'll give another name. Okay, it is a 1 bit, so it is 1 bit structure. Then here, as per earlier sessions, we are going to make this product category, that is all family of programmable device that we are going to use, that is a Spartan 3E. Device in that we are going to use is a XC3S500E, and package, that is a VQ100. Okay, speed, there are two choices, one is a -5 or -4. So we are selecting it as a -4. And then as we have selected top level source type, that is HDL. So this is disabled now here. And then synthesis tool, that is the XST, VHDL or Verilog simulator, iSim simulator. Now there is a one more option, that is a model sim, but we are going to select iSim simulator. So here that is we have selected, and preferred language, that is a VHDL. Okay, so we are going to write a code in a VHDL language. So we have selected this preferred language, that is a VHDL. Then we are going to store all the values in project file, so that we have selected, and then we are going for the next. Okay, so here there will be summary of this project, finish. Okay, and then you will see your project name in this hierarchy window. Okay, so here this is a right click on this your project name and click on new source, and then click on VHDL model. Okay, as we are going to write a VHDL code, so click on VHDL module and give the name to whatever program you are going to write. Okay, so now as we are going to use half adder circuitry, then OR gate in this program. So I am going to write all these programs in this project only, and then we will write a code for full adder. Okay, so let us first write a code for OR gate. So I will give name to file, that is a OR underscore gate. Okay, and then add this to project. Then next, click on next. And now, what are the input ports for OR gate? How many input ports are there for OR gate? As we are using a 2-input OR gate. So how many input ports will be there?
2 input, ma'am.
Yes. Okay. So let us give the name A and B. Okay, these are the input ports, and one output port, that is the out, that is, let us say, Y. Okay, so these are the ports. Let us keep architecture name as a behavioral, or we can make it as a DF, data flow also. So data flow. Okay, and then click on next. Okay, here also you will get summary of this new source. So that is a pin names, port names, then whatever is the type, source name, all that you will get here, and then click on finish. Okay, so you will get skeleton for your VHDL program. So where library declaration part is over already, entity declaration part is there because you have given the names to pins. So from that it has taken in this. Okay, now if you want, even though you have written something, okay, sometimes by mistake you have kept output ports as a input port, that you have not changed direction. असंही होऊ शकतं की तुम्ही चेंज करायचं विसरून गेलात आणि क्लिक केलं. ओके, सो जे काही चेंजेस तुम्हाला करायचे आहेत एनटीटी मधले ते इथं पण तुम्ही करू शकता आणि you can proceed. Okay, so now as we don't want to do any changes here, so let us proceed. We will write a code architecture here. So as Y, that is the output, so it is assigned to. Okay, and here very simple program is this because we are just using a simple OR gate, writing code for simple OR gate. So it will be A or B. Okay, semicolon, and then end of, sorry, this should be after begin. Okay, end of this. Architecture, and then end of the program, this program. Okay, so let us save this and let us synthesize it. So check syntax, as it is a very simple. So there is no single statement is there. So it will get compiled and it will syntax checking will be successful. That is, will be no doubt. So you can see that this is process check syntax that is completed successfully. You can go for RTL schematic. Okay, you can see this is the RTL schematic for ORCID. Okay, so that means we have synthesized this uh, VHDL code. Okay, so let us close this. And as we know that whatever code that we have written, that is the correct. So I am not going here for the test bench, but you can test this circuitry using test bench. But right now we will proceed further and we will write a VHDL model again for half adder. Okay, so half and adder, which is a, I'll give the name, that is a half adder. Remember that whenever you are giving a name to any file, it should start with a alphabet. Okay, and it will have only one special character, that is a underscore. You cannot use any another special character in this. And you can use digit letters also. So that will be this. So here we are giving a name to my entity, that is a half adder. Click on next. Okay, now ports for half adder, that is the input ports. Let us give the name A and B and sum. So I'll say it as a S, which is the output port, and carry output, that is a okay, and then click on next. You can, you if you want to change architecture name, you can. Otherwise, you can keep it as it is. Okay. So click on next and click on finish. Okay. And here you will get library declaration for this half adder, then entity declaration, and then in this architecture we are going to write now code. So as here sum, that is assigned to, what will be the expression for sum? A XOR B. Okay, and CO, that is assigned to A and so this is a half adder architectural code. So now let us save this code also. Click on here whenever you are going to check for the syntax of this in this hierarchy. Click on that source, okay, and then check syntax. Okay, now here this syntax, that is also successfully completed. So now let us proceed to write a code for full adder. Okay, so now I will click on again on the project name and then click on new source, click on VHDL module, and here name I am going to give this is a full underscore adder. Click on next. Okay. Now what are the ports for full adder? There will be three ports: input A, input B, and input C in, and output sum. Okay, so I'll give the name, that is a, okay, I'll use sum, and output again one more output, that is a C out. Okay. So this is a port declaration part. So click on next. You will get the summary and click on finish. Now here this library declaration part, that is completed. After that entity declaration part, that is completed. And now what we are going to do, we are going to write a architecture for this full adder circuitry. Okay, actually I will change here name for this. I will change this as a structural. Okay, and this also I am going to change now then. Okay, so here now I am going to use a structural modeling. So what I am going to do, whatever components I have, that I am going to use to model this circuitry, and that is why I'm going to use this half adder and OR gate as a component in this circuit. So what you have to do, you have to add this component after architecture sentence, okay, before beginning of this architecture. And once you declare what is your architecture, that means after this is you have to add component. So let us have component, okay. So this is a keyword, so you will find this as a in a blue color, okay. Now which component I want to add? I want to add half adder, so I will write half underscore adder, okay. And then however or how we are declaring entity, in the same way you have to declare a component ports here, okay. So port in the bracket, okay. So which ports we have used? We have used A comma B. These are the input ports which are of the type std underscore logic, okay. And we have output ports. There we have used output ports, that is S and CO, that are outputs which are again of the type std underscore logic, okay. End of this, sorry, complete the bracket and give a semicolon, okay. I will put this here. Now end of this component, end, okay. Now though our component has the name that is a half adder, but whenever you are ending this component declaration part, here it will come as a end and then just a keyword that is a component, okay. Semicolon. Then after that we have another component, that is a OR gate. So component OR gate port A comma B. These are input and type std underscore logic. Y output, which is again std underscore logic type. Okay, so end of this component also. Now besides this components, we require certain signals, because if you look at this, okay, so here we require in between connections also. That means this output of this half adder, some that should be connected as an input to this another second half adder, okay. So here we need certain connections. So whatever signals are present here, that we will call as a N1, N2 and N3. ओके. इथे जे काही कनेक्शन्स लागणार आहेत, म्हणजे आपण ही जी सम आहे ही आपण या इनपुटला कनेक्ट करतोय, तर त्या सिग्नलला आपण N1 म्हणूयात. इथलं कॅरी आउट आहे जे आपण ऑर गेटच्या इनपुटला कनेक्ट करतो ते N2, आणि या हाफ एडरचं जे कॅरी आउट आहे ते आपण N3 म्हणूयात, ओके. So I will declare these components, these signals, sorry, these signals, okay, N1 comma N2 comma N3. Okay. Then these are of std underscore logic. Okay. So these are the signals, that means they may be input or out, incoming or outgoing signal. So there is no need to specify its direction, but just signal. And what is the type of that? So we have it is a std underscore logic, so that we have mentioned there, okay. Now coming to the beginning of this architecture. So after begin, now we will write a code, okay. So now here we require 2 half adder and 1 OR gate. So we are instantiating these components in this program. So let us give the name to this first half adder, that is a HA1. Okay, so this HA1 is nothing but half adder. Okay, and then whatever are the ports of this half adder, that we are mapping with the ports of this actual full adder circuit. So for that we will use a keyword, that is a port map. Okay, and then so for the first half adder we are giving inputs, that is, sorry, this will be 1. So this is a and B, these are the inputs, and N1, this is the one output, and N2, that is a another output. Okay, so we will mention that. So A, comma B, then N1, comma N2. Okay, so in this way, that means it will consider this as a, for this half adder, A and B, these will be the inputs, and N1 and N2, these will be outputs. Okay, similarly, let us have another half adder, that is a HA2. Okay, this is again a half adder. Let us map the port. Okay, now here for this half adder, okay, Cin is the one of the input and N1 is the another input, and sum, that is the output, and here C out, that means N3 is the output. So we will mention in that way. So here Cin is the first input, then another input, that is a N1. Sorry, N1. Then output, that is a sum. Okay, and another output, that is a N3. Okay, and again we require one more component. Okay, so now if you write only OR, it will be in a blue color, that means it will consider as a keyword. But if you are writing in this way, OR1 or whatever, if you are using certain special characters, that is underscore or any letter, then it will be a user defined letter. So here we are saying it as a OR1, and then it is a component, that is a OR gate. So OR underscore gate, that is the name that we have given here. So that we are using OR underscore gate. Then we will map port for this. So port map, and here if you look at this, ports for this will be N2 and N3. These are the inputs, and C out, that is a output. Okay, so here it will be N2, comma N3, comma C out. Okay, and then close this bracket, semicolon. Okay, so that means we have done the connections of these components in this way. Okay, म्हणजे आपण इथे काय केलंय की यात हाफ ऍडरचे माझे 4 पोर्ट्स आहेत, 2 इनपुट पोर्ट्स आहेत आणि 2 आउटपुट पोर्ट्स आहेत. ओके, तो ए आणि बी हे माझे काय आहेत, इनपुट पोर्ट्स आहेत, आणि एस आणि C0 हे माझे आउटपुट पोर्ट आहेत. पण आता इथे मी जो काही फुल ऍडर साठी वापरणार आहे, तर त्याच्यामध्ये मला ए आणि बी इनपुट आहे, ते मी या हाफ ऍडरला देणार आहे. म्हणून माझे पहिले 2 इनपुट हे सेमच राहतील, ए आणि बी. पण माझं जे आउटपुट येणार आहे ते काय आहे, एस माझं काय मिळतंय मला इन टर्म्स ऑफ N1 मी कन्सिडर करते आणि C0 N2 म्हणून कन्सिडर करते. त्याचप्रमाणे याच्यामध्ये या दुसऱ्या हाफ ऍडर मध्ये मी काय करते, माझं एक इनपुट Cin आहे आणि दुसरं इनपुट काय आहे, N1 आहे, आणि आउटपुट काय मिळणार आहे मला, सम मिळणार आहे, आणि C आउट काय मिळते मला, N3 मिळते. तर त्याप्रमाणे मी मॅपिंग करून घेतलेलं आहे, म्हणजे इथं मला काय मिळणार आहे आणि ऍक्च्युअल काय असतं त्याच्याप्रमाणे मी ते केलेलं आहे, आणि OR गेट साठी सुद्धा केलंय. ओके, सो दिस इज माय code. Completely I have completed my connection. So this is completed. So end of this architecture. So that is the structure, and then let us save this. Okay, so this is now let us check for the syntax. This is completed, or we have saved it. Now let us check for the syntax. Okay, and check syntax, that is completed. So that means we have all this code that is correct. Okay, let us go for the RTL schematic. Now here you can see this. Okay, so you can check this connections as per whether it is as per this connection or not. ओके, तर इथे तुम्ही कनेक्शन्स बघा, इथे काय केलंय, ए आणि बी या हाफ ऍडरला दिलं, त्याची सम आपण या दुसऱ्या हाफ ऍडरला दिली आहे की जिथे दुसरं इनपुट आहे सी. ओके, आणि सी आउट आपण ऑर गेटला दिले, दोन्ही सम, दोन्ही हाफ ऍडर्स, आणि दुसऱ्या हाफ ऍडरची सम जी काही आहे ते ऍज अ आउटपुट सम म्हणून कन्सिडर केलं. ओके, सिमिलरली यू कॅन चेक इट हिअर. याचं जे काही सी आउट आहे इथे ऑर गेटला दिलंय, याचं पण सी आउट ऑर गेटला दिलेलं आहे, आणि ती आउटपुट ऑफ दिस ऑर गेट दॅट इज अ सी आउट. ओके, ए अँड बी इज अ गिवन ऍज अ इनपुट टू दिस हाफ ऍडर वन. ओके, and sum is connected to one of the input of another half adder, and Cin is given as the input to second half adder. Okay, and whatever is the output of that half adder, that is considered as a sum. Okay, so म्हणजे आपण जे काही प्रोग्राम मध्ये लिहिलं ते तुम्ही इथे RTL schematic मध्ये चेक करू शकता. ओके, so this is a RTL schematic for half adder. Now again if you click on this half adder, so you will get a whatever will be the circuitry inside that half adder. जिथे हाफ ऍडरचा आपण इथे फक्त बघताना ब्लॉक बघितला, पण त्याच्या आतमध्ये परत काय सर्किट आहे ते सुद्धा तुम्ही चेक करू शकता. सो दॅट इज अ RTL schematic, म्हणजे जे काही schematic असणार आहे that will be seen. Okay, so let us close this. If you want to check for technology schematic, that also you can do. So this is a technology schematic. Okay, ज्याच्यामध्ये परत बफर्स वगैरे पण ऍड होतील. So that technologically whatever is the requirement, so that will be added. Okay, I will close this, and the next part, that is we need to now check for the whether whatever code we have written, whether it is a correct one or not. That means whether there is any fault or not. For that we need to require or need to write a test bench for this circuit or this code. So for that I will click on this add new source. Okay, then I need to write a test bench, so I will click on VHDL test bench and give a name to this test bench as a full adder TB. Okay, and then click on next. Okay, add to project and click on. Now you can see that there will be three different sources in this wizard. Okay, so in this window you can see three different wizards. That is one for one is a sources, that is a one source is a full adder, then another one that is a half adder, and OR gate. Okay, but what we want to do, we want to write a test bench for full adder. So we will click on this full adder. Okay, that means we are going to associate our this new source test bench with this full adder source. Okay, if you click on this, so whatever is the test bench for half adder, that will be generated, and then you that will this circuit will be tested. But now we want to check a full adder, so we will click on this full adder and then click on next. Okay, then click on finish. So here this program window that will be open, which will have library declaration part, then entity, where entity will be just a empty entity where there will not be any port declaration part, that will be there, and then architecture of this entity. Okay, or this for test bench. So here a component full adder that will get added. Okay, so in the way the component how we have added now in the actually VHDL code for full adder. Okay, the similar way now whatever full adder code we have written, that will be considered as a component and that will get added here, and then all the signals that will be assigned to value 0. That means circuit will be resetted first to test, and then these outputs that will be and inputs also that will be considered as a signal here. As we are not going to use a clock, so I will delete this part. Okay, then beginning of this architecture. So here whatever is the unit under test, the ports of that will be mapped with the full adder ports. So that is assigned will be there. And then again there is a clock process definition, so I will delete that. And then stimulus process that we are going to write. Okay, so I will write a assign certain values to A, B as well as C in. Okay, so I have initially assigned A is equal to 0, B is equal to 0, and C is equal to 1. Okay, already we have made all these inputs that is equal to 0 by for the resetting of this circuit. So I will copy this part and just I am going to paste it here. I will change this as a 1, B as a 1, this as a 0. Okay, again I will copy this, I will paste it. Okay. So I will make now this as a 1. So I am going to use different टेस्ट vectors here. जे काही इनपुट कॉम्बिनेशन्स आहेत तेवढ्या सगळ्यांसाठी आपण टेस्ट करणार आहे. So I'm using that. I'm just copy pasting that and changing wherever required. Okay, now here at each time after that we have a wait statement. Okay, wait for 100 nanosecond, we have used that. That is for the making sure that this state will remain stable for 100 nanosecond. Okay, so for that we have used this. Again we have this clock statement here, so that we will delete. Okay, and then we have the initial last wait statement. That means whatever is the last value that will be hold for rest of the time. Okay, then end of the process and end of the architecture. So let us save it, then click on so click on simulation and then click on the test bench that you need to check. Okay, so now here in the process window, expand this iSIM simulator, check for the behavioral check syntax. The process is running and it is completed successfully. So now you can go for the simulate behavioral model. this window panel that is a waveform panel that will open. And now if you check for each of this, so here if you whenever there is a change, so that there I am clicking on this waveform. So initially we have all the inputs, that is a 0 0 0, sum is 0, carry is 0. Then when the scene is only 1, others are 0, so sum is 1, output carry output, that is a 0. Here B is 1, all others inputs are 0, so sum is 1, carry is 0. Here B is 1, scene is 1, so and A is equal to 0, so sum is equal to 0 and carry that is equal to 1. So in this waveforms also you can see A is 0, B is 1, scene is 1, sum is 0 and carry that is a 1. Okay. Next is A is 1, B 0, scene 0, sum is 1, carry 0. Next A1, B0, scene 1, so sum is 1, 0, carry 1. And then next A1, B1, scene 0, sum is equal to 0, carry is equal to 1. And the last, that is A equal to 1, B equal to 1 and scene equal to 1, sum is equal to 1 and carry that is also equal to 1. So here all that are conditions that are verified here, so all are correct, and that means whatever design that we have completed, that is a correct. Okay, so this is about the structural modeling of full adder set. Okay, now where this type of modeling is useful, whenever you want to use a certain circuitry so many times in your design, so instead of writing a code or repeatedly writing that code, you can write it once and then you can use it or instantiate it in your larger डिझाईन. ओके, म्हणजे कुठलंही सर्किट आहे, म्हणजे आता तुम्हाला जर परत तुम्ही मल्टीप्लायर डिझाईन करत असाल, ओके, तो मल्टीप्लायर मध्ये तुम्हाला परत फुल ॲडर लागणार आहे. तर एकदाच तुम्ही फुल ॲडर सर्किटरी डिझाईन केली आणि तो कंपोनंट आहे तो तुमच्या मल्टीप्लायर मध्ये परत परत इन्स्टंट म्हणजे एकदा इन्स्टंशिएट केला तर तुमचा कोड हा इझी होणार आहे. ओके, किंवा आता काही तुम्ही जेव्हा इमेज प्रोसेसिंग सारख्या ऍप्लिकेशनला जाता तर त्यावेळेस तुम्हाला मल्टिप्लिकेशन करावं लागतं. ओके, तुम्ही एकदा मल्टिप्लायरचा कोड लिहिलात की तो परत तुम्ही किंवा एकदा ॲडरचा कोड लिहिलात की तो तुम्ही परत तुमच्या दुसऱ्या जो कोड लिहिणार आहात प्रोसेसिंग साठीचा तर त्याच्यामध्ये यूज करू शकता. म्हणजेच ज्यावेळेस तुम्ही एखादं सर्किट एखादा कोड आहे किंवा एखादा कॉम्पोनंट आहे तो परत परत यूज करणार आहात रेफर करणार आहात त्यावेळेस तुम्हाला तो एकदाच लिहून ॲज अ कॉम्पोनंट म्हणून इन्स्टन्शिएट करणं हे जास्ती सोपं जातं आणि त्यामुळे तुमचं काम खूप इझी होऊन जातं. ओके, सो इन दॅट केस यू कॅन यूज दिस स्ट्रक्चरल मॉडेलिंग. पण जर सर्किट छोटं आहे तर त्यावेळेस आपण डेटा फ्लो मॉडेलिंग घेऊ शकतो किंवा जर त्याचं बिहेवियरल पण इझियर आहे तर त्यावेळेस तुम्ही बिहेवियरल मॉडेलिंग साठी पण जाऊ शकता. सो दिस इज अबाउट द स्ट्रक्चरल मॉडेलिंग ऑफ full adder circuit. Okay, so in some next circuits we are going to use a behavioral model. So initially we have used data flow modeling. Today we learned about structural modeling and in next some circuits we are going to use a behavioral modeling. म्हणजे तुम्हाला सगळ्याच सर्किट मध्ये आपण कसं वेगवेगळ्या पद्धतीने मॉडेलिंग करू शकतो ते बघता येईल. ओके, म्हणजे आता जर तुम्ही इथे बघितलं असेल तर आपण एंटिटी सेमच आहे. ओके, म्हणजे डेटा फ्लो मॉडेलिंग साठीच पण एंटिटी आपली सेमच होती आणि स्ट्रक्चरल मॉडेलिंग साठीची पण एंटिटी सेम आहे, फक्त चेंज कुठे झाला तर आर्किटेक्चर मध्ये चेंज झाला. ओके, म्हणजे एकाच एंटिटी साठी वेगळे वेगळे आर्किटेक्चर असू शकतात पण एंटिटी मात्र काय आहे सेम आहे, कारण आपल्या आउटपुट पिन्स ज्या आहेत त्या सेम आहेत आणि त्याच्यानंतर जे त्याचं इनपुट्स आहेत ते पण सेम आहे. ओके, सो दिस इज अबाउट द structural modeling of full adder circuit. So if you have any doubts you may ask. Okay, actually someone asked me to share Xilinx ISS software, so I have shared with him Xilinx with which will be which can be used with Windows 7, but Windows 10 software that I will be sharing with you. afterwards. Okay, so today I will share it with you, but it will require a space nearly about 8 to 9 GB, and so that much data also that will be required for you to download it. Okay, after that, what you can do, you can download that software, and also on a Xilinx ISC website, you make your you create your profile there. Okay, so log in with your college mail ID. ओके, तुमचा जो काही ऑफिशियल मेल आयडी आहे त्याच्यातून त्याचे लॉग इन करा, आणि जेव्हा तुम्ही हे सॉफ्टवेअर इन्स्टॉल करायला जाल तर तेव्हा तुम्ही त्याच्यासाठी वेबपॅक मध्ये जाऊन, म्हणजे त्यावेळेस मी तुम्हाला सांगेन ऍक्च्युली जेव्हा तुम्ही इन्स्टॉल कराल तेव्हा की तिथे तुम्हाला लायसन्स साठीचा अप्लाय करता येईल. ओके, तो पण त्याच्या आधी तुम्हाला झायलिंक्स ISCच्या वेबसाईट वरती जाऊन तिथे तुम्हाला लॉग इन करावं लागेल. और तुम्ही हे सॉफ्टवेअर तिथून पण डाउनलोड करू शकता, और आय विल शेअर अ लिंक. ठीक आहे, सो इफ यू हॅव एनी डाउट्स यू कॅन आस्क. नितीन, एनी डाउट?
No, ma'am.
अश्विनी? Okay, so if you have no any doubts, so we may stop here for today. We will continue with our unit, that is architecture of commercial devices, in the next sessions, and also with the same we are going to perform practicals also. So let us stop for today. Okay, enjoy Ganesh festival. And as today may be holiday, sorry, tomorrow there may be holiday, so not today. And enjoy Ganesh festival, eat lots of modak, and then after that in the next week we will continue with our further session. Okay, so
Okay, ma'am.
bye.